In this lesson, we're going to learn about the rule of three. The rule of three states that whenever you implement a destructor, a copy constructor, or a copy assignment operator, you most likely need to implement all three of these functions. And when I say implement, I mean whenever you need to implement. Okay, so several times we've implemented these functions. For example, if we look at image.h and image.cpp, we've implemented these functions several times just to have a print statement. Okay, this is not what I'm talking about. We're just trying to print something out so we can see when the constructor and destructor are called. No, what I'm saying is when you need to implement a destructor or a copy constructor or a copy assignment operator, when the program that you're trying to design or the object you're trying to design requires you to implement these functions. If you have to implement any one of them, then you probably have to implement all three of them. Let me show you what I mean. So image object, again, we didn't actually need to implement this destructor, so this one doesn't count. That was just so that we could print something out to the console. But the image manager, on the other hand, we did have to implement this function because the image manager is managing a resource, right? A memory resource. And because we call new in the constructor, we want to get this automatic memory management based on the lifetime of this image manager object. We have to call delete in the destructor. So we now have to implement the destructor for this image manager object. And so I'd like to demonstrate that because I implemented the destructor, I probably also have to implement the copy assignment operator and the copy constructor. Otherwise, I'm going to have problems with my code. Let me show you what I mean. So I've added a few lines of code to my main function here. I've added an initialize image function, which it's not really important what it does. The reason we're doing this is so that we can pass the image manager to a function. What it does is it just loops 10 times and it calls the setRandomPixel function on the image. So, we're going to create an image manager, which in turn is going to create an image on the free store. We're going to loop 10 times by calling this function through this image and set random pixels, and then we're going to set random pixel again. Again, these don't really matter. What really matters is that I'm trying to pass this manager object for which I had to provide a destructor into this function. Okay. And you'll notice that this is value semantics, so I am actually making a completely new copy of this image manager when I'm passing it to the function. Let's just look at what happens when I try to run this program. It seems pretty harmless. So our code has compiled. Let's go ahead and run it. And look at this. An image was created and destroyed, and I have a segmentation fault. Now, I thought I was doing a good job. I thought I was properly, creating a new image on the free store when I construct my object, and then deleting that image from the free store when I destruct my object. I thought I was doing things right, but clearly something is wrong. I'm getting a segmentation fault, which means I'm trying to access memory, which is not valid. So what happened? Okay, so let's try to figure out where exactly this program is crashing. So here we are, we've hit our first breakpoint now. We have our image manager object, which we are now just creating. Okay, so that's good, so far so good. And that image manager created a new image object on the free store, which is what we see here. Now we're going to call this initialize image function and pass the image manager into this function by value. Okay, so let's just go ahead and see what happens. I'm actually going to try to step into. Okay, so I've stepped into, all right. And so here I have, let's look at my call stack. So back inside of main, I had an image manager called manager, and it was referring to this image at this specific memory address. And when I pass by value, remember I make copies of things. So what exactly are we copying? Well, let's look. So I have a private data member, which is a pointer. Maybe you'll see, maybe you already see where I'm going with this by now. I have a pointer to this memory address. So when I create a copy of my image manager, let's look at Initialize Image. So I've stepped into this function. Notice that my image manager inside of this function also has that same memory address. So I've created a copy of this object, okay, and all of its private data members are just copied. So that pointer was also just copied. So now I have an image manager, the copy of the image manager inside of this function, okay, which has a pointer to the same exact memory location. So that's fine. There's nothing stopping me from doing that, and I can just step over this loop 10 times. And when I'm done, I'm going to return from this function call. Okay, so what happens when I return from a function call? Let's think about it. Image manager, the copy which we have inside of this function, not this one here in main, but this one we have here in this function, goes out of scope. Its destructor is called, and what happens when its destructor is called? The image that it's pointing to on the free store, that resource is freed. That resource is released from memory. Okay, so let's go ahead, step over. The image was destroyed, so that's all fine. Image was destroyed because I just called delete on it, right? But now here I am inside of main, and I still have this image manager, the one I had made a copy of, okay, when I called the function. And it still has a pointer to that same exact memory location because this one never had delete called on it, right? Or sorry, this image manager is still alive, okay? So it still refers to that same memory allocation. And remember what we saw earlier, when you try to dereference a memory allocation that has been reclaimed by the operating system, you get a segmentation fault. So this exact point, when I try to dereference that memory location, is where I get my segmentation fault. Okay, and my program crashes. Okay, so what do we do here? We have a problem, right? The fact that I am just allocating in the constructor and deleting in the destructor is not sufficient. And we saw that the problem really occurred when I started making copies of this object. So let's think about it. What should we do when we copy an image manager? What we really need to think about is when we copy an image manager, okay, this special object which manages a memory resource, when we copy this object, do we want to make a copy of the image that it's pointing to, or do we not want to make a copy of the image that it's pointing to? Now, if we decide that we don't want to make a copy of the image it's pointing to, we have what's called a shallow copy. Okay. If you have an object A which refers to another object R, and then you make a copy of A and call it B, and both of these objects A and B refer to the same object R, that's called a shallow copy. Okay, so you've made a copy of A, but its underlying data is shared with B. If, on the other hand, you make a copy of A, which refers to, again, some object called R, and when you make the copy of A and call it B, you also copy the underlying data object R and call it, something else S. Okay, so A refers to R and B refers to S. That's called a deep copy. Okay, in the context of our program, we have an image manager. And when we make a copy of that image manager, if we don't do anything at all, the default implementation of a copy constructor just copies each data member directly, and a copy of a pointer is just a memory address, so a copy of a pointer is just another pointer with the same memory address. That's a shallow copy. And if you think about the semantics of a copy constructor, everything else we've done so far in this class, a copy constructor has been a deep copy. So when you use a copy constructor, you should be making a deep copy of the object you are copying. Okay, and when we have a pointer as a data member, we're not getting that deep copy. Okay, and the problem occurs when we own that pointer. So the image manager owns the image it's pointing to. Why does it own it? Because it created it. It created it and it's responsible for deleting it. So this image manager owns this pointer to this resource in memory. So because we own this resource in memory, we have to decide how to properly manage it and what we should do when we're asked to copy ourselves. So the copy, all that is to say that the copy constructor for image manager, we're getting a segmentation fault because we're making a shallow copy when we should be making a deep copy. All right. So how do we properly implement a copy constructor so that we make a deep copy of our object? All right, so let's go to the image manager. Let's go ahead and create a copy constructor. So image manager. So here's the signature that we will need to use for that copy constructor. And now let's go ahead and implement that copy constructor. Okay, so image manager, : image manager. And then let's go ahead and provide the implementation. So we have to initialize image, okay? And the default implementation that the compiler was already giving us was basically just this, other.image. Okay, so it's just copying the value of that pointer, which is a memory address, into the new object's image pointer memory address. Okay, that's the thing that was causing us all this trouble. What we actually want to do is we want to create a new image. Okay, we want to create a new image on the heap. Okay, and which constructor should I call? Well, you'll notice that there is a copy constructor. So the default constructor that we had given it, you pass a string, which will be the name of that object. But what we want to do is make a copy of the image. So let's go ahead and invoke the copy constructor. And how do I invoke the copy constructor? I send a dereferenced, or I send a reference to another image. So let me go ahead and dereference the pointer other.image, okay, and pass that to the image constructor. This will invoke the copy constructor because I'm creating a new image, which is a copy of another image which already exists. Okay, I'm calling new, which will create this new image on the heap, and then return the pointer to that new image to the new image manager that I'm making. Okay, so hopefully that wasn't too confusing. It's kind of a lot to try to visualize as we're going through this. Let's go ahead and just compile and run this program now. Okay, so when I compile and run this program, no more segmentation fault. That's really good. Notice an image was created at this memory address. Okay, and a copy of an image was made. Okay, so we copied this image from this memory address and made a new image at this other memory address. Notice this memory address is different than this one. So we now have two images on the free store, okay, or the heap. And then eventually both of those images were destroyed. Let's step through this program and make sure we can see exactly where all of these copies are happening. Okay, so here we are. Last time we did this, we had a segmentation fault. So let's see what happens this time around. So I'm going to create my initial image manager. That's great. It creates an image resource on the heap on the free store at this memory address, the 60010 memory address. Okay, and then I'm going to call this Initialize Image function. Let me step into this because let's see what happens here. So notice the first thing that happens is I actually call the copy constructor for the image manager. Okay, that's the copy constructor we just barely implemented. So we know we're already on the right track. Okay, and let me step now into the function. And notice now I have an image manager at this address, 7000010. And if I switch back to main, notice the address is different. It was 760010. So I now have my image manager in main referring to this image, and my image manager inside of Initialize Image function, which refers to a separate image. So now it has its own independent copy. So I have now made a deep copy of the image manager. Okay, which is why when I go through all of these iterations, and in fact, let me just go ahead and return from the function. Okay, I have now destructed and step over this one line of code. So I have now returned from this function and destructed the image that I had created inside of that function call. Okay, and now I'm back to my original image manager, which is actually using this other image. Okay, the other image manager still has its own image which hasn't been deleted, so it's perfectly valid to use that image, and I can go ahead and continue my program and notice everything happened as it was supposed to. Now there's one more issue we haven't resolved yet. So we have fixed the issue of what happens when we try to copy an image manager. Let's go ahead and look at one more issue that we're going to have to deal with. What if our main function looks like this? So we're going to make a manager A and a manager B, and we're going to try to assign manager B to manager A. Okay, this is a copy assignment operation. We've learned about this. And when we try to do this, again, very similarly to what happened with the copy constructor, we're going to try to copy assign an image. Let me just go ahead and build, execute the main function, and again I get a segmentation fault. Okay, so I create an image A, that's good. I create an image B, which is at a different memory address. That's fine because I'm calling two different constructors here. So I have an image A and an image B, and then when I destroy image B, this image gets destroyed. And then something happens. When does image B get destroyed, by the way? It gets destroyed when I go out of scope of the main function. Okay. So something is happening here when I do this assignment that is causing the error. So let's go ahead and step through this code. Okay, so here we are inside of the main function. I'm going to go ahead, and these objects should not be initialized yet. Okay, so I'm going to go ahead and step over and initialize image manager A. It's got its own image. Image manager B, it's got its own image. There are two different memory addresses, which is what I expect. Now, when I assign manager A equals manager B, remember I'm going to make all the internal elements of manager A be equal to the internal data elements of manager B. So if I step over this one line of code, notice that the address of manager A updates to be the same as the address of manager B. And hopefully now you can see exactly what's going on. I'm about to go out of scope of the main function. Both manager B and manager A are about to be deleted. When I delete manager B, that's fine. The destructor will run and the image that it's pointing to will be deleted will be released back to the operating system. But then I will go ahead and try to destruct manager A, which is again referring to that same exact memory location. So it's like I'm telling the operating system, hey, you can have this memory back, and then I'm coming back and saying, hey, operating system, you can have this memory back. And the operating system says, wait a minute, I already got that memory back. You don't have access to that memory anymore. Segmentation fault. Okay. So what happens? Segmentation fault. Okay, and the reason that's happening is because I'm trying to double delete this image object. So what's the solution? Well, it very similarly to what we just did with a copy constructor, we now have to notice our programs is not correct. So we had to implement the copy constructor, and now you're noticing that we're going to have to also implement the copy assignment operator. Let's go ahead and add this copy assignment operator. Okay, let's go over here and implement this function. Well, the first thing we do is we should have the if guard, so we always want to check if this is not equal to address of other. Okay, so we don't want to do anything at all if we're trying to do a self-assignment. And remember, we always return star this from the operator equals function. Okay, so what we need to do, remember, I have this. This is a specific instance of Image Manager, and I'm trying to make it match this other instance of Image Manager, and I don't want to make a shallow copy. See, the default implementation that the compiler was just barely generating for us was this. This.image equals other. This is the default that was happening, but it's incorrect because what happens after this line of code is that both of the image managers, the other one and this one, both have pointers that refer to the exact same object. So if one of them is deleted, and or one of them goes out of scope and deletes that object from the free store, the other one will be referring to an invalid object. Okay, or an invalid memory address. So what do we have to do? Well, we have to do a deep copy, right? So what we're going to want to do is create a new image, okay? And just like with the copy constructor, we're going to want to use the copy constructor for image. Let's dereference it and make a new image, which is a copy of the old image, okay? And that's good, but remember, or think about it for just a second. Before this line of code runs, this object's image was pointing to a specific memory address, and now I'm just switching it to point to a new memory address. And if I do that, I've just abandoned the old memory address, and it's never going to be deleted. So I would be creating a memory leak if I did this. So the one thing I have to remember to do before I reassign this pointer to point to this new image is I have to remember to delete the old image. Okay. When the object I'm assigning to has a pointer and owns that pointer, what it should do is delete the object it's currently pointing to and then set its pointer to a new object that matches the one that the other one was pointing to. That is a copy of the one the other one was pointing to. Now that we've properly implemented the copy assignment operator, let's go ahead and see what happens, and hopefully we'll not have any more segmentation faults. Okay, so we'll go ahead and run our program, and there we go. I created image A, I created image B. I destroyed image A and then copy constructed image a new image B from a new image B from the original image B that was already there. Okay, and so now each image manager, manager A and manager B, are both referring to two different images called B, but they have different memory addresses. And so when those two objects go out of scope, when they exit main, both of the objects they're referring to are destructed. Now, this is great. I have just successfully created an image manager that properly manages the memory resource that it holds. Okay, so let's just look at this one, the header file. So it owns a pointer to a memory address. It creates that pointer in the constructor, and it deletes that pointer in the destructor. And because of the rule of 3, we've seen that because I had to provide an implementation for the destructor, it turns out that I also have errors in my code unless I also implement the copy constructor and copy assignment operator. So that is the rule of 3. Now there's one more thing I'd like to do now that we have this image manager. It's been confusing enough as it is to refer to an image manager and an image. But the image manager is really just a structure that manages a memory resource. Okay, so let's go ahead and make it generic. And instead of just managing images, why not manage anything of type T? So let's go ahead and make a template. Okay. Let's go ahead and make image manager a template. Instead of calling it image manager, what I'm going to do is call it a smart pointer. Okay, because it's a pointer to the heap that knows how to manage itself. Okay. So it's going to be called smart pointer. It's going to operate an object of type T. Okay, there's a few little adjustments I'm going to have to make. For example, the constructor is just going to have to take a raw pointer. So I'm going to create a new object and pass it directly into the smart pointer. Okay. The copy constructor will look like this. The destructor like this. Let's just go ahead and update. Now, because this is a template, I'm going to have to implement everything in place. Okay. So the constructor, let's just go one at a time here. What the constructor needs to do is it needs to initialize, and I shouldn't call this image anymore. What I should call it resource. Let's go ahead and just call it resource. Good generic name. So let's say, so I need to initialize resource to be that raw pointer that was passed into the constructor. Okay. If I call the copy constructor, resource needs to be initialized as a new T. Copy constructed from the other smart pointer's resource. Okay. The destructor is pretty straightforward. It just needs to delete resource. Okay. The copy assignment operator, a little more complex because we have to have this if guard if this is not equal to address of other, do some stuff, otherwise return, or afterwards return star this. And what's the stuff we need to do? We need to delete resource and then set resource equal to a new T copy constructed from the other resource. Okay. Now I like this one. What if we want to get a reference to T? How does this look? So if I dereference my smart pointer, this is what I'm saying. If I use the asterisk operator on the smart pointer, which will look like a dereference of that smart pointer, okay. If I dereference the smart pointer, go ahead and just dereference the underlying resource. And because it's of type T, what I'll get back is a T reference. And so this is kind of a clever little trick here, but it allows me to treat a smart pointer kind of like a regular raw pointer, and I can just dereference it and get back the dereferenced underlying data member. Okay, so this is a little bit complex here. We don't actually need image.h anymore. and we don't need string. And we don't need ImageManager.cpp anymore. So ImageManager.h, we could probably just go ahead and rename this thing. So let me go ahead and rename ImageManager.h to just be called SmartPointer.h. Okay. So it's a smart pointer class. Go back to main. There's no such thing as image manager anymore, but there is such thing as smart pointer. Instead of using an image manager, I want to use a smart pointer of image. Okay, that's the data type I'm operating on. I will need to include image.h now. So image.h. That should work. That should fix all of these errors now. And what I need to pass to it is a new image. Okay, that's what I need to pass. The raw pointer needs to go directly to it. So let's go ahead and make another one. Smart pointer of type image, manager B, pass a new image. Let's go ahead and also call the process image function on manager B. So the process image function is going to, I guess I renamed this process image. That's fine. Process image. It's going to actually take a smart pointer of image by value now. Okay. Now there's one more little fix we're going to have to do. So inside of process image, we're going to very conveniently just dereference the smart pointer. And we dereference the smart pointer, again, we get a reference to the underlying data type out of it. I need a semicolon here. Okay, so now, if I've done everything correctly, everything should still run. And I'm now doing a copy assignment. I'm also doing a copy construction. I'm constructing and destructing. I'm doing all of these things. And I should be able to just run this code and have everything work just fine. So let me run main one more time. And again, here we go. Everything works fine, no segmentation faults. And that should be obvious because all I did was just convert this into a generic template type object. And in order to really prove whether I've done this correctly or not, let's have the smart pointer manage something else. Okay, how about a string? How about just a string? We can place strings on the heap as well. Okay. String A, string B. The process image function, this doesn't really make sense anymore, but maybe we can call something called process string. Let's just use that name everywhere. Not really sure what we would do inside of this function. Let's just iterate 10 times and say dereference that string. And now we reference to a string object. And let's go ahead and concatenate the letter or the word hi to it. So that's fine, that will work. Okay, so I'm concatenating hi to my string every time I process it. And this code should also compile and run just fine, no issues. If I've correctly implemented this smart pointer as a generic template for managing a memory resource. And if this code does compile and run correctly, what that means is that my string objects are also being stored on the heap. Just go ahead and fix the declaration for this function. Okay, and we don't print anything out because now we're not using image anymore, which had all those print statements, but everything ran just fine. We could debug it and step through it. I'll leave that as an exercise for you.